Hello and welcome to the Computer Vision Festival, hosted by the AI Accelerator Institute, a global community of over 400,000 AI leaders and practitioners, all striving towards one shared goal: inspiring the next generation of machine intelligence. With expert presentations on the festival agenda covering everything from space exploration on Mars to self-supervised learning, you're in for a treat. If you have any questions for our speakers or want to connect with them further, then ask away in the comments sections of the video and hear them answered at the end of each session in our live Q&As. If throughout the day you're loving the content, then be sure to check out the AI membership plans, where you can get access to exclusive content in the form of interviews, reports and articles. Access all areas passes to all past and future events. You can also join our Slack community, which is home to more than 2,500 fellow AI, machine learning and computer vision professionals, and is full of dynamic conversations and contributions. So if you're not already a member, come and join us today. Sign up using the link on the AI Accelerator Institute website. I want to say a massive thank you to all of our sponsors and partners for helping us to bring the festival to your screens today. Our amazing speakers for contributing some awesome content, and to you, our attendees, for joining us today. That's it from us, so go ahead, sit back, relax, and enjoy the festival.
Hello everyone, this is Xiang Zhong. I'm going to talk about a few algorithms we have designed to improve user experiences in real-time communication systems. I'm going to talk about the use cases, the designs, and their accelerations. At the high level, the pipelines of a real-time communication system consists of pre-processing, encoding, transportation over the network, decoding, and post-processing. After the video is captured, it's going to be pre-processed for the sake of noise reduction. For example, it is then encoded to reduce the amount of data. Sometimes channel coding is also applied in order to provide some error correction capabilities. The data is then sent over the internet. At the receiving end, the bitstream is decoded and post-processed before being rendered on the screen. Post-processing is also to enhance the video quality and the viewing experience. The challenge is, in the real world, the network condition changes constantly, and sometimes the available network bandwidth can be very limited. This would significantly lower the coding bitrate at the transmission side. Last year, we measured some home network conditions in Silicon Valley. Packet loss of over 30% are not uncommon during dinner time. And we also saw packet loss of over 82%. And when this happened, the video bitrate dropped from the desired 2.0 megabits per second to just 0.2 megabits per second. And the video quality is severely compromised. The encoder has to lower the video resolution as well as the frame rate significantly in order to have some watchable, meaningful video sent over to the other end. Nevertheless, the viewing experience at the receiving end is compromised. In the next, we're going to talk about 3 things we have done in order to counter those degradations. One is at the front end to help achieve more video coding gain. The other two is at the back end as post-processing to enhance the video quality and the video fluency. First, let's look at how deep learning can help achieve more compression. When the bandwidth is low in RTC systems, video is coded at a low bitrate. The received video quality would be degraded, usually in the form of blurry. Our goal is to design an algorithm to achieve significantly more compression without degrading the video quality and without the need to adopt a much more complicated video coding standard. A much more complex video coding technology would challenge the mobile device computation power, which is very limited. A standard video coding technology is usually transform-based. The transformation is to transform the image space to the frequency spaces. The image X or a predicted residue of X would be transformed into the frequency domain Y. Y is then quantized and then entropy coded to form the output bitstream with a bitrate BR. The quantized value QY can be inverse quantized back to the transform domain as an approximation to Y. Y hat is then inverse transformed back to the image domain as X hat. Then the encoder is trying to minimize a loss function which consists of the difference between X and X hat plus a penalty item based on the bitrate of the output bitstream. The difference D is usually measured by MSE, mean square error, or MAD, mean absolute error. The problem with those measures is that they are not consistent with human visual perceptions. Minimizing MSE or MAD doesn't yield optimum perceptual video quality. This is because our eyes and the brain process the different visual information in different ways. Our eyes would apply more low-pass filtering at places with higher frequencies, and also will respond to the luminance change differently. We are less sensitive to changes at the bright or dark areas. Also, our masking capability is different to different distortions. We are more sensitive to distortions at the edges. Meanwhile, we are much less sensitive to distortions at complicated areas. In the figure on the right, the curve divides the whole area into two parts. Below the curve, our eyes are more sensitive to the distortions, and above the curve, any distortion is less visible to us. This property has been utilized by researchers in the coding community, and the method in this direction is called perceptual video coding. Some perceptual video coding methods try to define an explicit transfer function G, which transfers the image domain to the perceptual domain, so that the image x would be transformed to z, and x hat would be transformed to z hat. Now, the encoder would try to optimize the loss function of d z hat plus lambda multiply the br. This way, the optimized result is more consistent with our visual systems, and good results are obtained. Up to 10% of coding gain is usually obtained, which is very good. However, we still suspect the explicit perceptual function cannot capture the human visual perception properties accurately enough. There may still be redundancy left in the PVC coded bitstream. We know deep neural networks can capture visual information much better and may better exploit human visual properties and therefore provide more compression. We design a tiny convolutional neural network, and the training data set consists of a large quantity of image patches for a large variety of image contents. We associate each patch with the just noticeable distortion as the training data sets. We combine thus train neural network with the encoder, and the pictures derived from applying the neural network is virtually no difference from the one without applying it. Take a look at these two pictures. Even when we check the cheek area and highlight enlarge this area, we still cannot see much difference there. We performed more strict evaluation by inviting more than 20 subjects to participate in a double-blind subjective tests. 90 PVC coded and 90 non-PVC coded video clips are evaluated. The difference of the mean opinion score DMOS is calculated between the PVC coded video and the non-PVC coded video. A DMOS degradation within 5% is considered good in the literature. Our result shows that an average DMOS degradation less than 1% is achieved. Meanwhile, the average bitrate coding gain is more than 23%. In typical meeting sense, about 30% bitrate reduction is achieved. Let's take a look at the video. One side is with PVC on, the other side is with neural network based PVC off. The coding gain is 29% in these experiments. Very few people can tell the difference. Majority of people say they are identical. So, neural network has helped us achieve a meaningful, significant bitrate reduction. Next, let's take a look at how neural network helps with super resolution. When the video bandwidth is low in the RTC system, the video resolution may be lowered, and received video, if interpreted in a usual way, would look blurry and lack details. So our design goal is to design an algorithm to increase video resolution with significantly more details and clarity. In recent years, deep neural networks has helped achieve state-of-the-art in super resolution, especially the generative adversarial networks, GANs, achieves the most. The pictures shown here is a result from a state-of-the-art GAN model in the lower right side. In the middle is the result from the typical bicubic interpolation. In this experiment, a scale factor of 4 by 4, 16 times scale up, is performed. We can see that the right picture shows a lot more details than the middle one, which has virtually no details and very blurry. The GAN model consists of a generator and a discriminator. Either a real data or the generated data, GZ, is fed to the discriminator, and the discriminator is optimized to tell the real data is real and the generated data is fake. Meanwhile, the generator is optimized to generate data to confuse the discriminator. When the network is trained and converged, the discriminator no longer be able to tell which data is real, which data is fake. Despite its great success, there are still many issues in standard GANs. One of those is distortions. Shown here is result by the state-of-the-art GAN model results in the right. On the left is the Guangqiu's picture. We can see, even though a lot of details are generated in the right picture, but they are nothing like the Guangqiu's. The zebra stripes are actually in disorder. We come up with a new GAN architecture. We first analyze the properties of the deep neural networks and find that they should be globally Lipschitz continuous. We then apply the Lipschitz constraints to the model by adding an encoder L to the standard GAN model, so that the composited mapping L over G satisfies the Lipschitz continuous condition. The output of the encoder would be used to regularize the generator and force the generator to map a noisy image to a more natural image that is more visible to the Guangqiu's. This is further illustrated as the standard GAN model generating images with distortions in the high dimensional image space. When the encoder is added and required to satisfy the Lipschitz continuous condition, it forces the generator to be optimized to a map that can generate more natural images, as shown in the green areas. Numeric results has shown that our proposed method outperform the state-of-the-art. We measured the PSNR, structure similarity, and the perceptual index on 4 commonly used data sets, and those measures all outperforms the state-of-the-art ESR GAN model result. Take a look at the subjective quality. On the right side, the middle is the result from our result. Compared to the ESR GAN result on the top, the stripes are much more regular and closer to the ground truth as shown in the bottom. It's also sharper. Let's take a look at this video. As the line swipe from left to right, the super resolution DNN applies. We can see the blurriness is removed. The mountain, the water, and the stone, as well as the captions, are significantly enhanced. And much more pleasant to watch. Now, let's take a look at the frame rate of conversion. Again, when the network condition is low in the RTC systems, the frame rate may be lowered in order to send meaningful information to the other end, but the received video is with motion judder. The motion would not look smooth. So our goal is to increase the video frame rate with significantly improved video fluency. We make use of the UNet CNNs to compute optical flows, both forward motion optical flow and backward optical flow, and we make use of the deformable CNNs to create new pixel samples, and the final output interpreted by directionally depending on the desired interpolation time slot. We have a demo to show. On the left is received video at 4.2 frames per second. On the right hand side is upconverted video at 12.5 frames per second, 3x interpolation. And we can see the right hand side, the motion is much smoother. The right hand side is with motion judder. Now, let's briefly talk about how these models are simplified and accelerated for mobile devices. Neural networks are usually big models with a large number of parameters, and also takes huge computation power to execute. Shown here is the size in terms of the number of parameters. For lack of reference, we use MobileNet version 2 as a benchmark. MobileNet version 2 has 3.4 million parameters and is used for object classification. Our models have much fewer parameters, usually several order of magnitude smaller. Like, for example, the PVC model is more than 3 orders of magnitude smaller than the MobileNet version 2. We start from big models and make sure the big model achieves the desired result. Then we go extra miles to shrink the model, and eventually down to the point where most of these models can be implemented in middle or even lower range mobile devices, because a lot of our users are using mobile devices for RTC. As a summary, properly designed DNNs can help video compression, video super resolution, and the video frame rate of conversion, and help enhance the viewing experiences in RTC. And tiny models are necessary for RTC on mobile devices because of limited computing power. In the future, we are going to design more DNN models for RTC. Examples are noise reduction, deblocking, dejagging, and sharpening. Those processes will make degraded video look nicer and better. That would provide much more pleasant viewing experiences for our users. Thank you very much.
Hi there, Sean. So, just wanted to say a huge thank you for that presentation. Super interesting, super insightful. And welcome everyone to the Computer Vision Festival. I know I didn't jump on the last session, so I'll just take this opportunity now just to give everyone a warm thank you for tuning in today. And now we're going to open up the floor for some Q&A. So, why don't we start with Wendy's question? This is to you, Sean. So you mentioned the 82% packet drop rate. What percentage is needed to maintain a meaningful connection?
First, thank you, Jordan, and thank you much, Wendy, for the question. And it's a great pleasure to be here to talk about the RTC and the AI. And so it's actually depend on the level of the video. Right? If, for example, if you are sending like 720p at 30 frames per second, normally you would need like 2 megabits per second, or even 3 megabits per second for acceptable so-called good quality of the transmission, right? And if you are encoding like a 360p video, then normally you would probably need like 1 megabits per second, something like that. If network condition is bandwidth limited, so that you have a significantly lower bit rate than that, then the experiences would be significantly degraded, either in the form of like a very blocky video at low bit rate or a low resolution or low frame rate, or some combination of this effect would kick in.
Okay, great. So Wendy, let us know if that answers your question, but thank you, Sean. So moving on. Next, we have a question. So it's like kind of two questions wrapped up into two follow-up questions. So what is the biggest size of data set used in this experiment? And then what is the high resolution tried with this experiment? Is there any relation between resolution and compression ratio that you observed?
Is this for the first model or is this for the super resolution? Could you clarify? which this question is for. I have talked about 3 algorithms.
Okay, cool. So why doesn't hopefully I get this name right, Markandan, why don't you let us know which one you're referring to there? And then whilst you do so, just had another question come in. So WebRTC would require deep learning models to run in real time. How are some ways we can accelerate the runtime of deep models? I'll post it in the chat as well. So here's the question, Sean.
Yes, and first we have to make the deep learning model very small, and we would like cut off some number of channels and cut off the depths, and also we would make use of some other methods like architecture search, network architecture search, or we will also have a way to make use of the generative adversarial network to decide which channel and which layer contributed most, so that we can decide what can be cut off. And stuff like that, we normally would do several rounds of optimization, which branch, which channel contribute most, kind of like the attention model there, add attention there, and eventually we come up with a model usually with with number of parameters in the 10K around that level. Then we would also, when we implement it on the cell phone, we would make use of like the SIMD engine, right? So the cell phone usually have some SIMD engine. If it's on the we make use of the CPU to implement it, then we would just write some kind of assembly simply to accelerate it further. So all those things added up so that we can normally get less than 10 millisecond per frame processing time.
Perfect. Thank you so much. Really detailed answer there, Sean. So moving on to Rishabh. As you mentioned, less perimeters in the super resolution network. What frame rate can it achieve for non-GPU devices or devices which have integrated graphics?
Okay. Yes. If we are doing like 360p super resolved to 720p, then it would like take around 10 millisecond per frame by like a middle end to upper end cell phone, like iPhone 8, iPhone 10, we would get performance like that. Okay,
nice, cool. Thank you, Sean. So, Rishabh, hopefully that answers your question too. So, just one more, but we do have a few more minutes left. So, if you do think of a question, feel free to drop it in the chat comment box there. So from Mac, is there any published repo we can experiment with or contribute to?
And is this about like a publication about the matter?
Not entirely sure. So Mac, if you want to elaborate there, and then we can also tune it back to Markandan if you're still there. You did have some couple of good questions, but we just wanted to know which part of the presentation it was referring to. Max jumped in and said yes, so you was right in what you was thinking there, Sean.
Yes, we have a article uploaded to the archive.org, and we also have a link to our trained model for the super resolution, which you can verify or benchmark with your own method.
Okay, cool. Thank you, Sean. So you heard it there, Mac. So yeah, on that note, what we'll do is we'll wrap it up. What I'm going to be doing at the end of each session is posting the link to the next session, or you can just go back onto the main festival website and choose your schedule, as all passes now have access to all live sessions. So we've got a big day ahead. I'm going to post the link now, but one more time, just want to give you a huge thank you, Sean. Really cool presentation, super insightful.
Thank you very much. My pleasure.
Can you tell us the name of your publication?
Oh, okay. Yeah, so I will probably type it here. So it's called optimizing GAN through latent space optimization, optimizing generative adversarial networks via latent space optimization.
Perfect. Well, there you go. Everyone go and check it out. So yeah, we've got a big one next from Qualcomm. I've been promised that it's going to be a good one. So everyone follow the link. But yeah, thank you so much, Sean. It's been a pleasure having you present at the festival, and we hopefully see you again soon.
Thank you. It's a great pleasure to meet you. Bye-bye.
Thank you, Sean. Thanks to everyone for tuning in. Bye-bye.